So far, we've described cells under standard conditions. In this section, we're going to consider the dependence of the cell potential on concentration and therefore start to change the standard condition. Under standard conditions, everything has a concentration of 1 molar, and we would expect that the potentials are going to be based off of the standard potential chart that we saw in the back of the notebook. However, what happens when we look at changing that concentration and how that would affect moving the reaction either towards the reactants or towards the products? So we're going to consider something called Le Chatelier's principle. Which states that when you add stress to one side of a reaction, the reaction will proceed in the direction to relieve that stress. So what is classified as stress? So if you have a reaction like Al solid, this is the reaction we're going to look at here in a second, and 3Mn2 plus yields 2Al3 plus and 3Mn solids with an E standard cell of 0.48, indicating that it is a spontaneous reaction. If we have this reaction, it's spontaneous as written, and we add stress to this situation, and specifically the stress that we're looking is the concentration. We're talking about what would happen if we flood this system, meaning we add a whole bunch of like Mn2 plus aqueous in here. And instead of us starting with 100 Mn2 plus, we add 500 of them. Well, the reaction is not going to just continue to proceed as it would if it had 100. It's going to react and make a whole bunch of this product in order to get rid of all of those things that you just flooded the system with. So it's going to shift that reaction towards production of products. Likewise, if we add a whole bunch of product in here, like Al3+, it's not going to just continue to make product and leave it alone. It's going to start shifting it in the other direction. It's going to start making things go towards the production of reactants. So we're going to look at how does that affect the E cell, making it either larger or smaller, based off of change in concentration. So our first example, which is going to be letter A, is if we start with Al3 plus at a concentration of 2.0 molar, so that's twice our standard conditions, and concentration of Mn2 plus equaling our standard conditions, which is 1 molar. So we're going to double one of our product concentration. So if we had to predict what would happen, instead of us starting with 1 molar of each of these, we double the amount of Al3+. Well, then the reaction is going to tend to shift towards the production of the reactants rather than the production of the products. And remember that even though in Chem 1 we looked a lot at reactions going to completion, so reactants make products, products can also make reactants. So these reactions are reversible where this can reform that. So if we put a whole bunch of Al3+, we would assume it's going to shift towards the production of the reactants now. So I'm going to write some stuff here. This means that the concentration of Al3+ is higher on the product side. So these brackets mean concentration, which is molarity. PDT is product. And the reaction will favor the reverse direction. And reverse direction means instead of us going towards the right where reactants would make products, we're going to go from products to reactants. So if we wanted to compare the E cell and the E standard cell, So E cell means not standard conditions. And E standard cell, which is standard conditions, our E standard cell equals 0.48 volts. So the problem already told us that our E standard cell is 0.48 volts. We want to compare what happens if we change this. We're going to shift towards the production of the reactants, and then we would assume that the E standard cell is going to be greater than the E cell. So the E cell is going to be less than the E standard cell, because we're looking at taking some of these products, well, keeping that concentration the same, but doubling this, and instead of our reaction going as it's written, which is what the E standard cell would predict would happen, because it's positive, it's going to go towards the forward direction, we're going to make it go in the reverse direction, which would make this E standard cell drop down. So we're going to get less volts because we're not going to make as many products as this reaction is written. We'll compare this to a second circumstance, which is going to be letter B, where the concentration of Al3+, that's a product, is 1.0 molar, which is our standard condition, and our concentration of Mn2+, which is our reactant, we're going to triple, so we're going to put 0.3 molar. This reaction is going to favor the production of the products. So because we're flooding our system with Mn2+, we're going from 1 molar, multiplying it by 3 to get 3 molars of that. We're keeping our Al3+ standard condition, so we have a whole lot more Mn2+ that's going in the system. We're going to make a significant more number of products than we would have if we would have started with 1 molar of each. Therefore, the reaction will favor the products, and the E standard, let's write it the same way into this one. The E cell is this time going to be greater than the E standard cell because we're making more products, so the amount of E cell that we have, the amount of volts that we will be able to produce, is going to be significantly more. Okay, so let's flip the page. Now this, we're going to look at what happens when we have two different systems like in our galvanic cell, and then we have like non-standard conditions of concentrations in those cells. So it says galvanic cells which are constructed with two solutions of different concentrations in each compartment have to be calculated a little bit different. So if we look back to our original galvanic cell construction where we have our salt bridge, we have our metal electrodes, we have our concentrations in here, our solutions, we have a volt that's setting up, we have electrons that are moving from left to right. We're going to put an Ag, a silver electrode here, a silver electrode here, and in this side we're going to have 0.10 molar of AgNO3, and over here we're going to put 1 molar of AgNO3. So this time we have all of the same things. So we have Ag solid, both of them are silver nitrate. This is going to be our anode side. Obviously this is our cathode side. So everything's the same. The only thing that's different is that we don't have the same concentrations here. One we're starting with 0.1 molar, the other one we're starting with 1.0 molar. So in the system to the left, the anode begins with 0.1 molar solution of AgNO3, and the cathode, which is on the right, is beginning with 1.0 molar of AgNO3. Because the concentration of silver is greater on the cathode side, which is over here, the reaction is going to shift to relieve that stress. So it's going to shift to get rid of it and make our reaction go from the cathode towards the anode. So instead of our electrons traveling from left to right for anode to cathode, it's actually going to reverse this reaction. So we're going to go from the cathode to the anode now. So this is going to be slightly wrong. We're not going here to here. We're going to go the opposite direction. The cell described here, our concentrations are going to allow us to shift those. On the anode, the silver is going to corrode to produce Ag+. So this silver solid is going to break down off of this metal and make more Ag+ ions in the solution. So if we were going to measure the mass of the electrode before and after, This one on the anode side is going to corrode and lose silver ions. But the one over here on the cathode side, these silver ions are going to plate onto there, and it's actually going to gain mass. So we can look at the change of the anodes, of the electrodes as well over here. Okay. So let's look at a construction of one of these. So determine the direction of electron flow and designate the anode and cathode for the cell represented below. So now we're not necessarily going to have anode, cathode, right and left hand side. It's going to be based off of concentration. So iron for both of them, we're going to have 0.01 molar of Fe3 plus on the left side and 0.10 molar of Fe3 plus on the right side. So we have a greater concentration of Fe3 plus on the right side, we'll put a little salt bridge there, and a smaller concentration over here. So the concentration of Fe3 plus is greater on the right. So it's going to shift to get those out of the solution. So when it comes out of solution, it's going to plate onto this iron electrode. On the left-hand side, the concentration is lower, and the Fe3 plus will have to erode the electrode, and the electron flow will increase from left to right. Therefore, the E cell will increase higher than the expected E standard cell. So our electrons, again, are going to move from here to here, so we're going to have a forward direction. We're going to have to get iron out of this one and add it to this one. So in order for that to happen, this electrode is going to erode out, and Fe2 plus ions are going to go into solution. Over here, we need the Fe3 plus to come out of solution and plate onto this metal. So electrons or iron ions are going to come out over here. They're going to plate on over here our electron flow. So we'll have our anode and our cathode. Same thing. Okay, to practice this, you're going to do number 68 and 67.